Summing It Up is the last of a trilogy of books that Rob and I wrote, trying to explain mathematics that's at the cutting edge of current research to as general an audience as we could. And the genesis of the trilogy, well, first of all, we didn't plan it as a trilogy, but the first book started out in 1995 when I came to BC. At that time, I was at Ohio State. I came here and I gave a lecture on my current research. Rob took notes, and we decided to write that up as an expository paper for Mathematicians. And then a few years later, I began to think that it could be exposited even at a more elementary level to the general public. Not really, but that was our hope. And that led to this first book, which is called Fearless Symmetry. And there we took the mathematics that's required to prove Fermat's last theorem and broke it down really in a very elementary way, so that the first part of the book, you could read if you were 10 years old, in theory, and sufficiently interested in the subject. I can tell you more about how we planned and executed that book, but I think you're most interested in our latest book, which is along the same lines. So after that one, after a few years, we decided to write another one on a related topic, which is called the Birch-Swinnerton-Dyer conjecture, which is for certain cubic equations. And that's our second book, Elliptic Tales, which had the same format. And then a few years after that, we decided to write the third book, which is the one we're talking about today, called Summing It Up. And this one came about because in the first two books, there was a topic called modular forms, which is a necessary ingredient both to explain the Birch-Swinnerton-Dyer conjecture and to explain the proof of Fermat's last theorem. But it's a pretty advanced topic in number theory, and we didn't have room in those two books to explain it. We just mentioned it very quickly in one or two pages, and so we decided to write the third book, Summing It Up, to explain modular forms, which is a very important topic, not just for our first two books, but for many, many applications in number theory.
Each book is in three parts, really. I think they may even be demarcated as parts 1, 2, and 3, where the first part should be comprehensible to anyone. I'm not sure I'd say a 10-year-old, but certainly a college sophomore who's at least taken college algebra. And then the second part of each book requires some calculus, which can be omitted if the reader will take certain things on faith, but we feel freer to use some advanced tools in the second part of the book, maybe requiring as much math as a college senior math major. And then the third part of the book, we try almost to organize each chapter as if it starts in an elementary way, but then by the end will require some advanced tools, which you might have to take on faith. But we do try to get to some relatively sophisticated material by the end. And if you take some of the material on faith, we go through the arguments that show you how to build the rest of the structure.
I just want to add that our original idea for all three books was to take mathematics that was really at the edge of current research and break it down, as I said, in a very elementary way. And we wanted to imitate sort of what physicists will do. Physicists will take the most abstruse theories of the universe, what's going on now in their research, and explain it to truly general public by drawing pictures and waving their hands and using analogies. And that was the model that we wanted to follow. Now, we found we couldn't do it all the way. Because you can't picture most of the mathematics in as elementary way as a physicist can do. But that was the basic premise that underlies all three of the books.
Yeah, we were not going to try to tell cute stories about the lives of the mathematicians involved. We were actually going to try to discuss math as much as possible.
And also, I should say, when we started out, I mean, back around 2000, there weren't very many books of this nature. There are a lot of books for the general public about mathematics that told the cute stories or that talked about puzzles or various elementary parts of mathematics. But there was very little of this at this level. There's a lot more now, which I think is a very good thing for mathematics, trying to publicize it to more people. We had a little disagreement just now about whether this book is for 10-year-olds or for college sophomores. I think the truth lies somewhere in between. When we were writing the first book, I had my older daughter, who was about 15 at the time, and not particularly interested in mathematics. I had her proofread the whole first third of the book, which she did fine. And of course, she was especially motivated, but she seemed to understand that pretty well. And that's the idea behind all the books, is that really you should be able to give them to anyone who's interested, and they should be able to read the first part. And then if they've had a fair amount of college math, at least through calculus, they should be able to read the second part. And then the third part is usually more challenging.
Yeah, well, one of the interesting surprises to me is how many questions we've gotten from the general public about various aspects of the book. We've gotten we've been contacted by lawyers and by doctors asking for explanations about things in the first part of the book, which of course has helped us write the succeeding books as we learn what we should be explaining more carefully.
Although I would say that our average reader, based on the fan mail we get, has turned out to be, let's say, typically a retired engineer or physicist, or even a mathematician who's in a completely different subfield of mathematics, or also some hotshot high school or college students. Well, we wrote about number theory because we are number theorists, and we wanted to write about subjects that we felt comfortable with, that we could explain and be sure that we weren't just making stuff up. When it comes to saying why should the reader be interested in number theory, I don't think there's an answer to that question. I just read an interesting book called The Greeks by a great English classicist named K.J. Dover. And he's writing a book for the general public about ancient Greeks. And he says, I can't make you interested in the Greeks if you're not already interested. But if you are, they're fascinating to learn about. And I'd say it's the same thing with numbers and number theory. If a person is not at all interested, then our books are not going to change that situation. But if someone thinks that they might be interested, then I would encourage them to try reading, say, the first chapter or two of Summing It Up, because we want to promote that kind of curiosity among the public. And there's probably a lot of it out there that maybe doesn't get a chance to develop, especially given sometimes in school, sometimes mathematics is taught in a more dry way. And our books are meant to stimulate that kind of interest, if it's there potentially.
And I would add, I think number theorists have an advantage over most of the rest of mathematics in that we are talking about positive whole numbers, and everyone has some encounter with them. So our colleagues who study four-dimensional geometry have a much harder time convincing the public that four-dimensional geometry has any relationship to anything. But at least we're talking about whole numbers, and many people have heard about Fermat's last theorem. It's not that hard to explain. So I think we had an advantage. For me, the genesis of the book really was
of summing it up.
Of summing it up. For me, the genesis of summing it up, even before the question about modular forms, was just to talk about finite sums. And one of the things that's interesting is that there's a short formula to add up the numbers from 1 to 100. And this is one of those stories that we've all heard about. So there's a very nice way to add up 1 plus 2 plus 3 all the way up to 100 without actually doing the arithmetic, without doing 99 additions. And that's a very nice formula, and it's a formula that has multitudes of generalizations in some directions. You can ask other similar questions and get the answer. And then there are other questions that you can ask that are similar and not get the answer. And then, again, there are questions about squares, where you can get the answer easily, and then you ask similar questions about cubes, and the answers turn out to be horribly difficult. So just talking about these whole numbers gave us a handle on the first part of the book, just these very simple questions about finite sums. And then the second part of the book, we deal with infinite sums and try to explain why they're interesting. And it's not until the third part of the book that the modular forms make an appearance. They're a particular sort of infinite sum, which has some mysterious properties. I don't know if we entirely successfully explain why these things are interesting, but we give it a good shot.
Yeah, let me go into a little more detail, I think. So the first part of the book, as Rob just said, is devoted to finite sums. So there's two kinds of questions you can ask. If you have a series of numbers, how can you sum them up in a clever way? So for instance, the series of square numbers, 1 plus 4 plus 9 plus 16, how do you sum them up? And then you can take the cube numbers and so on. And that has a very beautiful answer that we develop in the first few chapters of the book. But then you can ask the reverse question. You can say, well, take a given number, like 100. Can you write it as the sum of two square numbers? Not a lot of square numbers, just two. That turns out to be a very interesting question. Which numbers can be written as the sum of two square numbers? And we answer that question completely in the book, although then it's starting to get more complicated. Then, as Rob mentioned, if you replace squares by cubes in that question, which numbers are the sums of two cubes, it gets much, much more difficult. So those are the one kind of finite sums that we're interested in. The other kind is adding up the number 1 to itself. So 1 plus 1 plus 1 plus 1. That sounds pretty easy, right? But you can ask, how can you group the ones? So suppose I take the number 4. I can add 1 plus 1 plus 1 plus 1. We call that 1 plus 3. Yeah? Or you could take 2 plus 2, or you could take 1 plus 1 plus 2, and so on. Those are called partitions of the number 4. And it's been a big question in number theory for well over 100 years. How many partitions does a given number have? So both of those questions can be repackaged in terms of certain infinite series, infinite sums of numbers that we discuss in the second part of the book, and they turn out to be answered by the theory of modular forms, which are particular infinite sums that we discuss in the third part of the book.
For me, has a simple answer, and that was definitely JSTOR, because so many of the ideas we were talking about were relatively elementary for mathematicians in the first two parts of the book. And so because they're also deep, there were many different ways to describe the proofs, many different proofs. JSTOR turns out to have a tremendous collection of journals about mathematical pedagogy. And there were many ways of approaching these ideas that were new to me, seemingly were new to readers as well. We get email that say, I didn't know this before. So that was just really thrilling to see that these ideas must be very deep because there are so many different ways of approaching them. So that was far and away the most helpful thing, that there were papers from 1950 that maybe no one had looked at in 50 years that had some very, very clever ideas.
The other thing I've been helped with by the libraries here is with interlibrary loan. So although we don't have a super comprehensive collection of math books and journals, whenever I have to look for something and I ask the library to find it for me, they can get it for me quickly, and that's been very helpful. I must say that as time goes on, current research is more and more deposited in this thing called archive, where mathematicians will put their papers before they're even accepted by journals, and everyone can go there to see them. But the library here has been very supportive of operations like archive and similar other things, trying to get free access to research, and that's going to be more and more important as time goes on. So will there be a fourth book? That's the question, and I guess there will.
There's a fourth title.
There's a fourth title. So this is a trilogy, as it turned out, and I think we really have covered all the bases. So we were discussing for a while what we might do next, and I think it'll be something quite different. It will be concerned, I think, if this plan comes to fruition, we've just begun talking about it, we will be studying the concept of transforms. So a transform is a procedure where you take a given function and transform it into another function. Now, in the abstract, it sounds like stupid or, or like, what does that mean? And of course, it can only really be explained by examples. But the main example, the most important example is called the Fourier transform, which some people may have heard of. And the Laplace transform is another one. And then there's the Radon transform, which is used in CT scanning. And Fourier transforms are used in computer science and all over the place. So we're thinking of that topic, and I haven't really discussed it too much with Rob yet, but I think I'd like to get away from this three-part method and try something different. I'm not sure exactly what, but yeah. And what's the name we decided?
From cosines to CAT scans.
Metamorphosis from cosines to CAT scans. That's our working title.
Yeah, and it struck me as a worthwhile thing to write about because engineers use these tools every day. And yet here I tested my wife, and she had never heard of a Fourier transform or the idea of a transform at all. So it seems as if there's something that one tiny segment of the world uses all the time. When you talk to Siri, Siri is answering because of Fourier transforms. And yet most people have no idea. They've never heard of this concept of a transform. So there should be a book there.
Yes, and it does, and it has a good punchline, I think, at the end, because everyone now has to have a CT scan for one thing or another. That'll be sort of a good ending point. And you prove the theorems about CT scans. They just come right out of the theory of Fourier series, Fourier transforms with some added material. So yeah, I think it should be interesting.
Yeah, it's a beautiful case where the math was there way before the technology for a CT scan was there to take advantage of it.
Yeah. So why did I become a mathematician? Yeah, and I'm interested to hear Rob's answer. I don't know his answer. I guess it was a combination of two things. One was I was just always really interested in numbers. And then when I learned about algebra, I was really interested in algebra. My father was a physicist, and so he taught me a lot of things at home way before I learned them in school. And I would do things, I guess it's kind of nerdy, like for fun, I would solve two equations and two unknowns, and see that the answer really worked. So that always fascinated me. Then when I went to, so I figured I'd always be a mathematician, and I majored in mathematics in college, but in college I was interested in other things as well. And I toyed with doing other subjects. I was very interested in philosophy and in Greek classics. But I felt that mathematics was so difficult or so abstruse that it was really, you could really only learn the deepest parts of mathematics by being a mathematician. Whereas, forgive me all you classicists, but I felt I could keep studying classics and philosophy and so on without having to be a professional. So it was a little bit of a path of least resistance for me.
I think I partly inclined to echo Avner's answer about least resistance, which is that I liked math. I kept doing it. And even though it's really hard, I always managed to find a niche that I could fill to keep going. So I just never ran into an obstacle. I think if I had run into an obstacle, I'd be a wine salesman now. I don't think I'm as gifted as Avner, so Greek was not going to come into the picture. And I probably would be a good wine salesman, but I was just very lucky that even when the stuff got hard, there was always another course I could take that was easy. So
but
I
were
found my
you
way
doing
through.
mathematics as a little kid?
Oh, sure. I added up the squares. When the first time I got a calculator, I added up 1 plus 4 plus 9 up to 625 or something, and I checked that it worked with the right formula. I don't know if I was checking that the formula was right or that the calculator worked. I hadn't thought that through carefully, but I definitely did that the first time I got a pocket calculator, and it was just so exciting that the formula was right.
So it was really great to work with Princeton University Press, and I hope they'll continue to publish all the rest of our books. The way that happened was kind of funny because I guess I'm a little bit diffident, and I didn't think we could really get a book published at all,
Yeah.
And but Rob is a Princeton fanatic, And he said, well, let's send it to the press, which we did. And they gave our first book, it really went through the ringer. They sent it to 4 different referees, and we completely rewrote the whole thing one whole time and then kept revising it. But we had a lot of support from our editor, Vicki Kern. And then after the first book was fairly successful, she's continued to encourage us to write the others. And she's just been really great to work with.
Yeah, she could easily have given up based on how bad our first draft was of the first book, but she saw something there and helped us find it.